Okay. Hi, good evening, everyone, and good morning to people outside India. It's a nice evening today, and we're really happy to have a lot of experts with us in quantum technologies. Today, we're going to be talking about quantum optimization for industry. And in this, we'll cover what is optimization. We're also going to cover hardware aspects of it. We'll also give you a tour of the system on which some of this optimization was done on. And in the end, we'll also talk about purpose. And to do this, today we have experts with us, and maybe I'll allow everyone 2 minutes to just introduce yourselves so that the audience gets to know you. We'll start with you, Professor Byrd. Please go ahead.
Hi, I'm Greg Byrd. I'm a professor of electrical and computer engineering at North Carolina State University, and I'm director of our quantum initiative, which includes a relationship with IBM, IBM Quantum Innovation Center at NC State. I'm also involved with the IEEE in quantum. I'm the vice chair of the IEEE Quantum Technical Community and have been an organizer in several different roles of the IEEE Quantum Week conference or the IEEE Quantum Conference on quantum computing and engineering. And my background is computer engineering, so I'm not a physicist. I'm not a mathematician. I like to make things run. I like to build things and get the most efficient use out of hardware as we can. And I've been working in quantum for about 7 or 8 years now. It's been very exciting to learn the new technologies and new techniques that you have to figure out to run things well on a quantum machine.
Thank you. It's a pleasure to have you with us. Thank you so much. I'll now go to you, Rishi. Rishi, please introduce yourselves.
Hello everyone. I'm Rushikesh. I work as a quantum solutions architect in Qkrishi Quantum, and I'm primarily the algorithms guy. So, my main job is to design structure-aware algorithms for real constraint problems. So, I worked on diverse problems like the supply chain that we are discussing right now, portfolio optimization. I also developed QML algorithm for fraud detection, and my interest lies in how different type of problem and how we can solve them, developed resource aware structured problem algorithms and problem solutions for them. Yeah.
Thank you, Rishi. I'll now go to Biman. Biman, please tell us about yourselves.
Yeah, thanks, Venkat. So my name is Biman Chattopadhyay. So I am co-founder and CTO at Quanfluence. At Quanfluence, we are building a photonic quantum computer, and we also build quantum-inspired hardware around photonics, which can deliver optimization solution to QoS and combinatorial optimization problem. So, echoing Professor Bird's view about uh, uh, doing something which can be used right away, I am from an electronics engineering background, so I am not a physicist. And again, my interest had gotten into me, and so we started Confluence in 2021. Before that, I was with Synopsys and Texas Instruments and building hardware and IPs there. But here I have now gotten in this interest, and my role, I would say, as a CTO is to make the physics make real and be touch and feel out of that. So that's what I do at Confluence.
Yeah, that's very exciting. So we'll talk to you more. Thank you. I'll go over to you, Yasser. Please tell us about yourself.
Yes. So I'm Yasar. I am working as a research software engineer at Qkrishi. My research area is majorly AI optimization, and recently I have taken up quantum optimization. Uh, Domains which I span over with my research are LLM. I work in NLP also, and it's been like 8 months now working with Qkrishi. and it's been a wonderful journey till now.
Thank you. Nice to have you here with us. Okay, over to you, Sangram. Please tell us about yourself. Yes. You're on mute.
Yeah,
Yes.
yeah,
Yes.
yes. So, yeah, everyone, hello. Uh, 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 I am Sangram Despande, a PhD student advised by Dr. Byrd, and it is my great honor to be his student, uh, working in the working in the area of quantum algorithms for distributed quantum computing. And before joining PhD, I was working as a senior research software engineer at Qkrishi, where I led team, which you can see, which is working on quantum algorithms now.
Thank you. Thank you,
Yeah,
Sangram.
yeah,
Very nice.
yeah.
So let's get into it, right? So optimization problems lie at the core of modern industries. They include supply chains, finance, logistics, manufacturing. A lot of these, problems in nature are combinatorial, explosive, lots of parameters to consider. So today we are going to be talking about problems that this team has solved. One of the few teams in the world to look at these large scale problems. And this team brings both hardware and algorithms expertise. Okay, so that's the exciting part of what we have for you today. So let me start out with a question to you, Professor Byrd. Can you explain what is optimization? So we have a lot of students who have joined us today. Some of them might just be getting into using quantum computing, and some of them, for them, this is like the first time they're exploring or learning about optimization. So can you tell us a little bit about what is optimization? uh, Give us an overview of what it is and what kind of real world instances are there which are computationally hard and which are optimization problems.
Okay, I will do my best. Uh, so optimization in general is really just what it sounds like, which is how to find the optimal setting, the optimal set of parameters to give you a good solution, the best solution if you're really doing optimal, the best possible solution. And what do I mean by solution and parameters and all that? If we take a problem, the fundamental thing we do is say, well, how do I know whether I have a good solution to this problem? I've got all of these different numbers that I can play around with. How many, in terms of supply chain, for example, how many units do I order? How many of this kind of unit? How early do I need to order it? How much do I expect my clients to buy? And how much inventory should I have? All of these numbers, all these values that I'm trying to figure out. And I'm doing my hands because we think of them as engineers, little knobs to tweak, right? What are the how if I increase this, what happens to the system? Does it mean I have too much on hand, I'm going to lose money, or I just want just the right amount? So that optimization is the figuring out what the setting on all those knobs ought to be. And how do I know whether I've got a good solution? So we have something called a cost function, which, once I have set the knobs and I look at the system, the cost function tells me whether, what the cost or what the profit of that set of knobs will be. I predict that using some mathematical model. And in general, there's lots of different mathematical constructs for do this, and people that are in operations research and industrial engineering work on, very fancy mathematical ways of describing this. But if for our purposes for this conversation, we sort of narrow down a little bit to what we call combinatorial optimization, then all of the choices we have are binary choices, right? Do I set this knob to 1 or 0, or we have integer values that we represent in binary. And so again, we have a mathematical model which can be expressed as a matrix vector sort of mathematical operation. We can think about it as we can even think about it as Boolean logic of if this is true, is that a good solution or not? And all of these different combinations of knobs lead to a very large space of possible solutions. And the challenge of an optimization algorithm is to find the best, right? That's the ultimate goal, is find the best set of values for these variables. But sometimes we settle for a pretty good one as opposed to the absolute optimal one.
Thank you. That was a very good, simple, and clear explanation. I think that was very useful to get us started today. So now, Rishi, I'll go to you. Can you tell us how does industry solve these problems? Like Professor Byrd explained, why do we need optimization? What is it all about? Can you tell us how industry is approaching these problems? How do you computationally solve these things?
Yes. So the beauty is like, all these optimization problems are relevant to their own industries. So basically, like, uh, I can broadly categorize, these industries or these domains. Like, for example, let's say if there is a small scale industry, or a small, operation unit or something like that. So they don't go for such heavy maths. Okay. So they don't go for using some models or mathematical models or something like that. So what they do is like, human expertise. For example, let's say there is a guy who is managing, school buses and routes to travel the students to their schools and colleges and all. So there is no need, but there is definitely this is an optimization problem, because you need to manage and get every student on time when the school starts. So there are, like, for this kind of small scale problem, there is no math. Human expertise solves it efficiently. And there are and if you if there is a little big problem, it goes as rule based. So people tend to use Excel. They add some rules. Okay, I need to send it in certain days and all, and they get a certain schedule and kind of thing. So these are very common in like MSME industries or small scale optimization, sorry, operational units. Okay. So then there is this heuristics and approximation method. So, when Professor Byrd was talking about this mathematical models, so there are certain algorithms that we have designed, like all the experts in the industries and academics and all. So some are like greedy approaches, greedy algorithm, local search and all. So when there is a little bit math is needed, okay. So all these kind of heuristics and approximation methods gives us a solution. Most of the time, it is not needed to be an optimal one, but it gives us a good solution. Okay. Then I can say third kind of industries where heavy math is required. And now this math is increasing, this kind of, because we humans are increasing in population. Okay. So the consumption needs, okay. And people now are wanting something from there, something from here. And production is also to produce a good quality product. Now, all things are coming from here and there and assembling somewhere and delivered to us. So here most of this, you cannot manage it with some basic algorithms. You cannot manage that with some rule based or human expertise, definitely. So here this mathematical optimization solvers are being needed. So such are known as linear programming, or mixed integer linear programming. And this is solved on classical solvers, using SAP and Gurobi, Cplex. IBM has one, right? I think that, yeah. So these are done. And there are these enterprise platforms, right? So these are using like ERP and supply chain management systems. Okay. So these are broadly we can categorize, like right now in industry, this is happening, and we are using such kind of models. And I think I'll quickly give a context to all the students, like what is the problem that we are have tried to solve here. So they'll have this reference, okay, whatever we are discussing ahead. So I'll just in 2 minutes, I'll quickly give this reference. Uh, yeah. Yeah, so can you share the PPT as well? Yeah. So basically, I want to say like what kind of problem we studied here. So it was the data that we had was of a skincare industry, skincare industry. It was a you know there were different kind of SKU, that is stock keeping units. Okay, like hair, skincare, lotion, and all. And there were this multiple products. So then multiple planning is involved. So there were different planning decisions we need to make, and we need to balance production, inventory, and demand fulfillment. So overall, like this was the problem. How much you need to produce over the capacity limitations and all. And if you just scan this QR, maybe you can direct to the article and download it and read it. Uh, yeah, I think you can just stay, Yasser, a little bit on the less previous slide for a second. I think now most of the guys have maybe have scanned or something. Yeah, let's go ahead. So, uh, what we are trying to achieve is to reduce the overall operational cost. Yeah. So we are trying to reduce overall operational cost of production, inventory management, and everything, and supply, and also we are trying to maximize profit. This is the whole agenda here, right? So we need to balance. It's not like you are just doing cutting off anything unnecessarily. We need to think what to meet this demand. We need certain kind of SKUs, we need certain kind of products, right? So we are trying to keep a balance between how much to produce and how much to manage and store. Like a simple example I can give is like there is a, let's say, a sweet shop, and there are two types of sweets, let's say gulab jamun and rasgulla. So let's say if the sweet shop owner has produced more than demand, whatever it is, okay. So what happened is certain amount of his gulab jamuns are kept in the stock, and now like they are not getting what you can say being sold. Okay, so he did that for maybe like some for event or something, festival is going on and all. But later what is happening now, like he has produced more, so it like he cannot throw it away, and now he got to know that other sweet is getting much more in demand, so he doesn't have the capacity to produce and hold it, and like he has got a loss of it. So we need to always get this balance. Okay, and we did same thing we did with this different product, different SKUs of this skin scale startup industry. Okay, so the main thing is to produce stable and feasible plans. So, uh, and the constraint means the things that we need to check that holds these problems together. Okay. So like, for example, what few of the constraints that we used in this research was, so limited production capacity. Okay. So you cannot produce any capacity if the solver says to make to more profit. Okay. Or the algorithm says, so you need to put a constraint that the maximum capacity I can produce in a certain amount of time is like 2000, 3000 units, 4000 units, or something like that, right? So this was specified for the algorithm. Then there is inventory, how much I can store. So you cannot store more than your what we can say inventory, more than your storage unit or something like that. And there is a demand, like whatever the demands that industry is getting. We want such and such units, we want so and so product, kind of these SKUs and all. So we must fulfill that demand. That's how you are in the game, that's how you are in the industry. And all these decisions are discrete in nature, so that's all this result in the combinatorial problem, right? So, and the results that we get here is uh, that we got after solving this problem is a proper production and inventory plan, total cost over time. We also we benchmarked with the classical methods, classical algorithms that I described earlier on, and some classical solvers as well. And we got to know whether all the constraints that we have, whether it is being satisfied or not. So we did that all analysis, put it together, and we got this solution. Yeah, I think yeah. So
Thanks a lot, Rishi. That was a very good example that you gave us. Okay, so now for the examples you gave, I'm going to ask questions from Sangram and Yasar. Okay, so Sangram and Yasar, question to you. So Rishi just showed us a set of problems, right? One problem he showed,
Mhm.
and he showed how it is solved. Now the big question is, there is classical techniques, then there is quantum
Yeah.
techniques, right?
Mhm.
So what are the limitations of classical? Why do we have to go to quantum at all to solve some of these problems? Where is it struggling, the classical techniques? Can you throw some more light on classical optimization versus quantum optimization?
Yes, sir.
Yes.
Sangram, I'll just
Okay.
introduce to the problem, and
Mhm.
you can continue with me.
Okay. Mhm.
So, sir, the first thing is, it is the problem which we have selected. It's a multi-period SKU allocation problem. It is NP hard. It is highly dimensional problem. It has very high dimension, and it is a constraint heavy problem. We are dealing with capacity limits, SKU count, risk exposure. We want diverse SKU selection throughout each period. So these are the constraints that we need to satisfy to get it. And the problem with the current solver, the exact solver, is that we cannot scale this much constraint into that. So we have this classical baseline selected as PSO, particle swarm optimization, genetic algorithm, and colony algorithm. Now, we all know that all these three, PSO, GA, and ACO, they handle non-linearity very well. It means they can work with relationship that aren't straight. They can work in very proportional way, or even if the relation is not very well defined, they can work with that well. Second, they don't require a convex objective. They they we can say that they don't assume there is a single best smooth solution. Even if there is a maximum local minima and those things, they'll try to find out the best out of it. And third is that they scale better than exact optimization solvers. So to meet these all the constraints and like constraint which we have defined above, we need to fairly formulate what the cubo approaches have been formulated with. So we need to formulate a profit maximization equally formulate with the cubo formulations. So with this setup, we move to the PSO and these algorithms. So PSO, it looks really good. Like uh, we haven't violated any capacity constraint. We have enforced top five performing SKUs over all periods. But the PSO algorithm has only selected 83 SKUs. Most of the periods, the capacity remains like unused. The capacity is not used to the maximum what it should have been. And the final profit which we got is just about, I guess, 4 million something. So it is that not did PSO break formulations or anything. The real question which we needed to answer in this paper was, why did it stop short? Why did PSO didn't perform well? So uh, it's an issue not with the formulations or anything, but it's the issue with the binary PSO itself. Velocity updates don't translate cleanly in discrete decisions, the decisions made by PSO. And on top of that, if we see the cosine similarity matrix, which are to the right side of the paper of every approach, we can see there is a lot of redundant stock keeping units visible. So the selection is not diverse, as the capacity is not being fulfilled. So there are very redundant stocks selected. Now with genetic algorithm, if we go, we have selected 271 SKUs. It's a great selection SKU unit, and profit also jumped to 11 million something. But the main catch in that was, it performed really well under capacity, same formulation and everything. But after optimization was performed, in GA we perform an automated step to remove the excess SKUs so that the solution becomes feasible. and that results were very sensitive. It might be change in mutation or a crossover a bit, but overall it is very noticeable in that. And to highlight about the cosine similarity, it was same. It was dense cosine similarity matrix. Like the redundancy was also there, and the profit though looked good, but there was some kind of redundancy observed there. We can like with the GA thing, we can genetic algorithm, we can say that it had a strong exploration, but the feasibility isn't built in search itself. So we tried another approach, ant colony algorithm. It selected around the same units as genetic algorithm, SKU units, and the profit was 10.5 million something. But the same problem was repeating. Like it was not getting redundant. We were getting redundant pairs a lot, and we are having cosine similarity matrix was too dense for it. So if we put this all together, the results we got with the Cubo formulations were far more, way better than what we got with this formulation. Sangram, you can highlight more on the next part.
And Yasser, just one
Yes,
thing,
sir.
you could show the paper once, after
Yeah,
Sangram, just so that people
yeah,
can see
definitely.
the paper you're
Definitely,
talking.
sir.
Go ahead,
Yeah,
Sangram.
yeah. So as Yasser have given me the opportunity to talk about the limitations of classical solver, I would like to put uh, some light on the uh, uh, on general classical solvers like our interior point optimization methods or some other like Newton methods. So the problem with these methods are they highly rely upon the dense matrix factorization, and as these solvers need to manipulate large matrices to solve the system of equations, and as when the number of variables and constraints grows in this, the memory requirements explode, especially if the matrices are dense in that case. Even when solver is polynomial uh, time in theory, but the number of operations per iteration can make large problems impractical. Uh, so, and then there is another thing called as curse of dimensionality. So, as the number of dimensions, as the number of decision variables increases, the solution space expands exponentially, and exploring it becomes slow and expensive, and covering enough of that space could be true optimal. Uh, I mean, it would be very hard to find true optimal. In many real world problems, mm, the landscape, sometimes the solution gets stuck in the local minima or saddle points. And in the classical gradient methods, where like simple gradient descent often gets stuck in the local minima, because yeah. And to make this matters first, uh, imagine a dense matrix of size n cross n that can lead to very high compute cost, uh, and very high mm, like the uh, requirement of the memory to solve such problems. So when we step back, uh, whether we are talking about meta heuristic like particle swarm optimization or some more traditional solvers, uh, the challenges aren't just minor inconveniences. Uh, they are packed into the very structure of these methods. Understanding these limitations is crucial when we want to select or design a problem optimization strategies for complex problems, complex real world problems. Yeah.
Thank you. Yeah, nice. So now I'll come to you, Biman. And a lot of people told me they're really looking forward to this segment by you. Okay, so yes, so we're now going to talk. You're going to please tell us about the quantum inspired optimization hardware that on which all of this runs. the coherentizing machine, what is the Quanfluence system about. Maybe you can, I think you're also going to give us a demo of it. So we're really looking forward to this one. So over to you, Biman.
Thanks, Venkat. Yeah, you're putting a lot of expectation on me, and let me see how I can do. I'm going to just share a small presentation, just to give a little bit of introduction about this, and then switch to the video. I'm sure that will be probably of more interest, but I will still just give a little bit of intro. I'm sharing my screen. I hope that it is visible. Share. Okay, I'm sharing my whole desktop. Is it visible?
Yes, yes, yes. It's
Okay,
visible.
great. Great. Okay, so yeah, at Confluence we are building a photonic based quantum computer as well as a photonic inspired quantum inspired and photonic machine. So we have two complementary quantum solutions. I would say one quantum and one other is a quantum inspired optimizer. The quantum computer solution, that is a full stack photonic based quantum computer, and that leverages the power of photonics in order to create qubits and a scalable quantum room temperature quantum processing. Uh, its availability is mid 2029. So the thing is, what can we bring to the table today? And there, a quantum inspired optimizer comes in. And that is built on a coherent Ising machine technology. And I would try to show a little bit of both so that we get the overall journey, that we start from a quantum inspired hardware, have usability today, industry usability today, and then we seamlessly move on to the quantum realm. So, starting with optimizer, given the key focus here is on that, and I think we talked about the set of things where optimizer comes in. So, I just thought that before I go to the hardware, I also want to just bring in a couple of other angles of like some proof of concept usage of quantum optimization that we have been working on. For example, commodity procurement in auction. This is another example of optimization. If on a classical solver, it trying to do optimize the wool procurement in an auction system, 100 to 120 sellers out of 1500 sellers you have to select. You have to satisfy, once you buy the wool, where to keep it, the constraints, and then the quality and the cost minimization. A typical optimization problem. And it's a combinatorial because you have to select or not select. You cannot say I'm going to need half of it or one fourth of it. You either get to select a bale of wool or you don't. So it's a combinatorial optimization problem. Solving it on classical, the scale of the problem is something that you cannot solve directly, and then you have to then make it sequential. That leads to non-optimum allotment. So answering one of the questions, Venkat, that why these other solutions are relevant is because it is not just a choice. If you have to go there, if you have to do it in parallel, and then once you do that, then you can have better utilization of capacity, because now you are getting the solving the problem at the global level, better cost and faster speed. This is one of the example that we have done on that machine. Another POC example is boot packing of a car boot packing. Again, this was more of solving the problem formulation was done by the OEM. This is a typical problem where in design of cars, the usable area of the usable volume of the boot is to be, and you cannot calculate it by finding the overall volume. Usable volume is calculated with respect to how many bricks can you fit there. It's a given dimensional object, and then that becomes a pretty big one 120,000 size problem. And then again, solving that on the machine, it gives 15x faster solution. I mean, from several days, it comes to less than 2 hours on this kind of a problem. But then this is not fully optimal. I mean, that was one of the point which Professor Byrd was also mentioning, that sometimes you have to live with non-optimal at a certain scale of problem. But then the thing comes in about a quantum classical hybrid options that you quickly do a rapid prototyping, and after that you can do more additional things on top of that with the initial solution. CVRP, very typical examples of almost when you start with optimization, one of the first thing you do is CVRP. It's like the trying to optimize delivery routes from a central depot to multiple locations. And again, solving it on a machine like this, you get a significant speed up. This was solved on multiple problems from the CVRP lib. 10x, 20x faster solutions at big, large scale problems. Job shop scheduling is another example. So, again, these are typical problems that we solve in this thing. So, machine comes the quantum machine can do variety of problems. And what I'm going to do is that to specifically answer your question about the hardware, right? I have a small video. I'm going to just play that would show a little bit more talk about the hardware. And also one of the co-author of the other paper, Nikhilesh had made part of the video. So I think you'll get to see him also in the video. So I'm going to switch to that, okay? Mm. Yeah, it's really getting one series for one. This is inspired by autonomous and is highly scalable and fault tolerant and it's very energy efficient because this can function mostly at room temperature. We have made quite some progress on our quantum computer and we have the second version of our photonic IC rating. We have a few sensors which are also being sold as individual components, including the single photon detector, the valence homodynamic detector, and we also have a quantum random number generator. The applications of this technology are endless, including drug discovery, financial analysis, cryptography, and more. Let us take a look at a video that gives a higher understanding of how a quantum computer will work.
Welcome to Quanfluence. We're building a photonic quantum computer, one that's designed from the ground up to scale. This is our system. It's modular. Now let's dive deeper, module by module. We start with the quantum light source, squeezed light pulses generated in photonic ICs. These are the core resource for CV quantum computing. We generate them either using bulk optics or on chip. This light is then passed to the resource state generator or RSG. Here, squeezed light pulses are reflected off a quantum dot cavity system and converted to Schrödinger cat states. Short pulses of detuned laser light are used to prepare the quantum dot in a superposition state and to read out the state after reflection. Next, light enters our interferometer and delay line network, implemented on photonic chip attached to optical fibers. This is where the cat states are bred to form a robust CV photonic qubit, the GKP state. Optical fiber spools are used for delays. After computation, we measure the quantum states using a balanced homodyne detector. This lets us extract information about the quadratures, the key observables in CV systems. We've built our own low noise, high quantum efficiency detectors. Finally, everything is coordinated by a custom electronic chip and control software. This is where MBQC is done. Right now, we do this in FPGA. This is not a concept or simulation. This is a real system. We've taped out and measured 4 photonic integrated circuits and 2 electronic ICs. Our photonic chips, detectors, and logic are being tested with early customers. So if you're solving complex optimization or simulation problems, we'd love to talk.
It happens that some problems need a matter to solve. So we have a coherent edging machine to solve these industry scale problems that are too big or too complex to be solved by a classical computer. So our coherent edging machine uses something called edging technology to solve these problems by doing a directed search on the solution space at a high speed, giving a higher quality solution than existing classical technologies. Some of the applications are supply chain optimization, vehicle routing optimization, optimization in the telecom and airline industry, and more. Let us take a look at the coherent edging machine. This is the coherent edging machine. This is connected to a password, and as we can see, it is being interfaced by a laptop. The problem being solved here is a capacitated vehicle routing problem. This problem is converted to something called a QBO, quadratic unconstrained binary optimization model, and sent to the machine. Let me explain the components of this. This is an FPGA board programmed to do high-speed matrix multiplications. This is ADC die, which does analog to digital and digital to analog conversions. This is a photodiode developed in-house. This receives light and converts it to analog signals. This is a laser driver with a laser acting as a continuous source of light. This light goes through these optical fibers to this intensity modulator, which can modify the intensity of the received light based on the analog signals that it receives. So when the QBO is received, a set of high-speed matrix multiplications happen on the FPGA board, yielding digital values. These digital values are sent to DAC, which converts them to analog signals, sending these signals to the intensity modulator. And based on these signals, the intensity modulator converts the intensity of light to a different value, and the new light is sent to the photodiode. The photodiode converts this light to analog signals, and which is sent to ADC, which converts them back to digital values, sending it back to the FPGA board. This is one loop of the edging machine, and this happens for thousands of iterations to solve the problem at a high speed. This was about the coherent edging machine. Let us take a look at our lab where all of this is built. This is our lab on the 3rd floor of our office, and we begin by showing you our optoelectronics lab. This here is the characterization and test setup for our single photon detector product, which is also shown here. And we have a setup using pulse laser and coincidence counter for checking the dark counts detection efficiency and after pulsing for these detectors. This is the prototype of our coherent edging machine computation product. This is under pilot projects with some early customers. This setup is the development of a quantum random number generator. And here we are characterizing our custom IC with a high bandwidth and low noise TIA built in an advanced BiCMOS process. This is the entrance to our optics lab through an air shower. Inside our optics lab, we have this setup, which is a free space OPO to generate squeeze light at 1550 nanometers. This setup also uses our own high quantum efficiency balance detector to characterize the squeeze light. Beyond this, on the other part of our lab, we have our photonic IC characterization setup.
This is a class 1000 clean room enclosure where bare dies of photonic ICs can be characterized. And there are two setups to do fiber to pick alignment here. In this setup, we have placed one of our photonic integrated circuits under a microscope, and fiber alignment to the chip is being performed in this setup. The light going in and out of the chip is transported using optical fibers in these fiber arrays. And this setup also has an automatic alignment loop, which can optimize the fiber to chip coupling efficiency automatically. This is another setup with manual alignment. And this is our setup to characterize switch light from a photonic IC. And in this case, this photonic IC is inside this package here. So the fibers have been bonded to the PIC.
So that was a glimpse of our cutting edge lab situated right here in Bangalore. We are building this revolutionary technology from the ground up from India. So if you are looking for solving complex optimization problems or high efficiency sensors, or you are just a curious person driven to do something in the quantum domain, log on to quanfluence.com and feel free to reach out to us for anything quantum. Thank you.
I think with that, I'm going to hand it over to you, Venkat.
Thank you. That's exciting, and all the best with all the work that you're doing. Thank you. So I'll now get back to Professor Byrd and Rishi. Okay, so can you tell us what kind of optimization problems are good for quantum? So are there such a class of problems that you think which you say are good for solving on a quantum computer? How do you pick these problems?
Rushi, I'll let you start with that. I think you've got more experience of looking at different problems than I do. Why don't you start?
Sure, sure. So basically, this is a very more good question, I would say, because a lot of industries are trying to experiment, a lot of academic researchers are trying to experiment with such problems. So the problem specifically we can say that are good for quantum are like which has more combinatorial possibilities of solution. Okay. So, for example, if the problem scales, if you try to increase the variables, if you try to increase the variables means you try to input more and more data. If you try to input more and more constraints, okay. So, and increase the data. A simple example can be like if you want to select optimal number of stocks, or just say not optimal, if you want to select most top performing stocks, okay, when you're trying to invest, okay. So you have a budget constraint and everything, and let's say the possibility of that solution is the universe of that stock, 2 raised to universe of that stock. Let's say if this is Nifty 50, it is raised to 2 raised to 50. Okay. So that's how if you scale up, like if you go to 100, then if you go to 500, so there is an index called as Nifty 500, right? In India. And similarly, there is S&P, I think, in US. So basically, when you increase such kind of, variables and the solution space, okay, so classical solver fails there. Okay. And here is where quantum can give us the better advantage. Because, for example, I'll give a simple example of variational algorithm like QAOA. Okay. So this algorithm is designed to, get like explore where like there are two things as cost Hamiltonian, which Professor Byrd just explained us what it does, and there is a thing called as mixer Hamiltonian, which is additional, which allows us to explore this solution subspace and reach, or what we can say, escape this local minima. Local minimum is like it is a quality of solution. So how Yasar told us, like, there is this 4 million profit, this solution has adhere all the constraint, obeyed all the constraint, but this solution is not good. Like it appears us to be good. It appears us like it is a good quality solution, but it is not. Okay. So quantum algorithms and quantum computing is expected to escape such local minimas and give us the best solutions. And there are now multiple algorithms going on, and the top of two are variational algorithm, one of which I described. So wherever in any industry, wherever there are huge number of possible combinations, quantum has a good knack of yeah, what we can say, solving those problem, or very what we can say, very complex problem. Even the solution subspace is low, there are less variable, but there are too many constraints. Okay, there are too many what we can say, constraints that we are putting in the objectives, like and everywhere. So there also there is a high possibility that quantum computing can give us an advantage over there. So, for example, in this problem that we tried to solve, so this is a multi-period planning problem, right? So, as I give an example about that sweet shop and everything, so you need to maintain these all things that I mentioned, earlier, that capacity, lead, and everything. So these all are interconnected, and the problem, the algorithm that the structure of this algorithm that we developed was, dense. Okay, like how Sangram told us. So here, this particular Confluence machine, particularly the architecture of this machine and the structure of this algorithm, combinedly escape several local minima. Okay, several solution which are appears to be us that they are good solution, but they are not. Several local minima and give us the best profit and best solution, and that is how you are trying to solve and getting this advantage over there. So to get this advantage or to solve such kind of problems, you need a good hardware and definitely a good algorithm or good software. And with the help of this combination, you are able to escape these local minima and solve these problems, and which classical can only be dreamed of. Yeah.
So I guess I would add to that, or another aspect is that Rushi mentioned is the constraints. And if you're asking me what the best for that matches sort of current quantum hardware, are things that don't have many constraints, or things where the decision variables or the data that you have are sort of influence each other in a sparse way, right? So that if you change this variable, it doesn't affect everything else, but affects just sort of some other things. Because the more dense that you have, the more interactions you need between the qubits that are representing your solution, and the more operations you need to sort of let that influence propagate throughout the system. Those are harder and harder to do. The other thing that I would say is that some of the constraints involve kind of mathematical calculations, and the quantum computer is not the fastest thing to do multiplication, for example, right? You only want to do that if that's really necessary in the kernel of your problem to do that mathematical operation. So quantum computers are really good at creating and sampling from a very large set of possible solutions, but then a lot of times we rely on the classical data to interpret those solutions and then guide the quantum computer to create a better set of states that will kind of tease out that good solution for us. And so the fewer constraints you have, the better likelihood that you're going to get a good answer from a quantum computer currently. But there are a lot of people working on how to encode constraints in a more efficient way and how to deal with things. But I think for a long time that the optimization in particular is going to be this very tight coupling between classical computation and quantum resources. I think that's the way to go. So that's my 2 cents.
Thank you. I think that was a very good answer because it clears a lot of doubts in everyone's minds. So now we come to a very important part of this, which is a lot of the students who are watching are asking, how do I prepare for the quantum job market? Okay, so Professor Byrd, this is a question specifically for you because you've been in the academia for a while, and I'm sure students ask you this question. And you're also, probably it's top of your mind. How do I make sure the students are prepared for the job market which is emerging or has already emerged? So what is your number one advice in this?
Well, the first thing that I would say is that you don't have to be a quantum physicist to work in quantum computing for a number of reasons. One is that the principles of quantum mechanics that we use in quantum computing is a subset of all of quantum mechanics, right? You don't have to know, um, you know, everything about the universe in order to make a computation work. And so you can focus in on the discrete part. You can focus in on the parts of quantum mechanics that you kind of need to understand. But really, as computing technologists, what we're interested in is how is information processed, and I think you can learn that without having to know everything about quantum mechanics. The other thing is that there are a lot of the quantum industry has been built up around the physics, right? They came up with these great ideas and experimental techniques to show that it can be done. And now what's needed is a lot of engineering and a lot of software that physicists are not particularly trained to do. And so we saw in the lab at Quanfluence, all of the optical and all of the electronics and all of the FPGA work and all of that stuff are things that electrical engineers and computer scientists and people in material science, right? They can contribute a lot to this, making the doing exactly what Quanfluence is doing, right? Taking the idea and the technology and making it reproducible and reliable and less costly, and all these things are going to be what drives the industry. We have sort of the demonstration now, and a lot of companies are working and trying to get faster and faster and better and better. They're going to rely a lot on engineering and software, people that know how to design large scale software. Um, so there are a lot of opportunities. So I would say you train in the classical way that you normally would to be a good engineer, to be a good software developer, and you learn about quantum as you do that. So you understand how information is processed, and you understand what the challenge is as well as the promise of the quantum computing uh, industry may be, and you sort of just make yourself prepared to find that opportunity that you will find in the quantum industry if that's what you're interested in.
Yeah, thanks. I'll now come to you, Sangram. Sangram, you've been in the startup for a while and now you're doing your PhD, right? So,
Yeah.
what would be your advice to students on how they should prepare, and maybe you're like a role model, okay, for a lot of young people today. So, tell us what path you followed and what is your
Okay.
advice?
So, about me, I have pursued my bachelor's in computer science engineering, and then I was passionate about doing something in quantum. I was not knowing what to do, so I just approached to different people, different companies, and then I got to work with the startups in India, and then I started working with Qkrishi, and I mean that was very beautiful journey of my life, I would say. And as Venkat sir have precisely mentioned that I am a student now. Previously, I was a industry expert, but as of now, I'm coming to you as a student, but also with some experience as a senior research software engineer at Krishi. So I get to see both sides. Okay, so what's it's like learning in my current phase, and obviously prior joining the startups and preparing as a student, and what industry actually looks for. So, and fortunately, I also had some, I also had chance to be on the other side of the table, that conducting a few interviews for Krishi, uh, and that experience gave me first-hand experience. That experience gave me first-hand view of what companies are truly looking for. both the technical skills and the mindset. I would like to emphasize on the mindset, as Professor Bird have clearly mentioned that not all uh, quantum computing experts need to know about quantum mechanics and all, but they should have some mindset to learn on the go, to uh, navigate through the problems. They should have the mindset to solve solve the different problems which they might not have trained to solve. So they should have all that mindset, and to make a candidate stand out. When it comes to what the quantum industry looks for, it's actually quite clear. Based on my experience, companies are looking for professionals who can translate complex quantum concepts into the practical solutions, like software algorithms, systems that can actually be deployed and be used. And it is not just about theory or research papers. The industry wants people who can build tools, develop quantum algorithms, and contribute to software or hardware platforms like the Quanfluence that have real-world applications, whether it's optimization, cryptography, drug discovery, or any other domain of quantum computing. The goal is to create products and solutions that can be scaled and obviously used by many clients and ultimately deliver some value, some real value, both scientific and commercial. Yeah.
Thank you.
Yes.
Yeah,
Yeah.
thanks.
That's all from my side. Yeah. Thank
So,
you.
Biman, what would you say it takes to transition from academia to industry? So somebody comes fresh from college. What are the two, three things? I know Sangram mentioned a few things, but what would you add to that?
I think the breadth of knowledge is something that is very important, because one of the things is that there are multiple languages, I would say, that we speak in the community. Physics has a way of physicists have a way of speaking things. We speak in a certain way. Even within engineers, electronics engineers versus the photonic engineers would have different ways of making the same statement, and that connection between them is what actually allows us to actually translate things. So that is a breadth of knowledge, and I absolutely like Professor Bird and Sangram, both of you pointed on that, right on that point, that I guess the thing is, like, basic theories should be what should be the focus on. Like, don't worry about did I learn so much of quantum or not. Do I know information theory enough to actually do something in quantum? And the other thing is, see, in quantum, things are not all figured out. I mean, there are a lot of figuring out has to be done. And that would require it's not that I'm going to study this and come and just start working on that. You have to, a lot of things has to be figured out on the go while you are doing stuff. So, which would mean that get your basics right, and then as we go, we learn more and more things. So that I would be the biggest thing. I mean, don't be too worried about, okay, did I learn this part of the thing or not? I mean, do you know something very strongly at what you have studied, and then you can obviously scale from there and learn more stuff. That's what I would say.
Thank you.
Exactly. I would like to again talk about my experience in Krishi. I did things which I never trained for in Krishi, like the web development, the software product development, which I never trained for. As a computer science engineer, we had got some introduction to Java and all, but I never did as a product. But in Krishi, I got a chance to work on that. I learned on the go, and I guess it was nice to. It was a wonderful journey for me to learn new things, deploy it, uh, do some updates, then again do like uh, to make it available for the users. Like that was wonderful part. Yeah, and
Thank you.
I believe that students should have mindset to learn, then they would be definitely be able to succeed in the quantum career.
Sure. Yes. Okay, so now we come to the fun part, okay, which Biman, you said you were looking forward to. So, Okay, so we'll ask a few rapid fire questions to people and then we'll go into a little bit more of detail. So, Professor Byrd, AI or quantum?
In the near term, AI.
Okay.
There's a lot of exciting things happening in AI that's happening now. And quantum's still going to take a bit to get to a scale where it can make a huge impact. But yeah.
Okay, thanks. So, to you, Biman, research paper or product launch?
Sorry, I didn't.
Research paper or product launch?
You know, my answer is obvious product launch. That was easy one. Thanks.
But that was too obvious. So now another harder question for you. Okay. So superconducting or photonic?
Okay. I would say the near term and the short term, the longer term view. On the near term, definitely superconducting, because it can show something now and you put them together and you can show a path. Photonics is something that I see on a longer path. And I also think that superconducting is going to benefit from photonics for connecting multiple superconducting. So it may not be antagonist to each other. It might be a complementary technology that moving forward. That's how I see it.
Nice. Okay. So, Yasar, you're the youngest person here. So, to
Mhm.
you, a question which a lot of young people keep asking me: algorithms or
So can you just repeat? You were
algorithms, algorithms or hardware?
okay. I would say efficient algorithms, uh, because if we design algorithms better, taking in consideration, we can deploy it on any hardware, but it should be efficient algorithm.
Hmm. Okay. And now, Sangram, to you. Okay. So
Mhm.
you, this is a question. I mean, yeah, startups or big industry?
Okay. So first of all, to start with your career, startups are the best because you need to learn, you need to be on the every side of the team. Like you have to be uh, junior researcher, you have to be product developer, you have to like be everything. And if you turn your mind someday, you may join a big industry. But I'm definitely sure that startup would be my first choice,
Okay.
at least for a couple of more years.
I see. Okay. Okay. Nice. So, Rishi, question to you: have you been able to explain quantum to your parents?
Yeah. So, but I would say like only 50% my mother got it, to be
Okay.
honest. Yeah. But I need to explain it in very, what you can say, a child's terms. And I feel like, yeah, I feel like I'm not getting the actual, who quoted it, but if you're able to teach it to kid, you are able, the full concept and something like that. So I got that feeling after, explaining to my mother, although she got only 50 to 60% of it, what I work today. So, yeah, like before I explained to her, she was just saying, he works in IT or he works on computer or something he does. But now she is able to just say like, okay, what actually my son is doing and all. Yeah. Yeah.
Very nice. Okay. Thanks. So Yasser, do we have some questions we can pull from the web, uh, from the YouTube live? Uh,
Yeah. Yeah, I think we have some questions. I'll ask. Okay, on behalf of you.
yes, please.
So there is Karthik T. Karthik. I think he's asking like, is the next big thing in other quantum computers, like all of the quantum computers? And I think Biman, you can answer it.
Sure. I think the interesting thing about this quantum technologies is that each of the technology has their benefits and challenges that has to be addressed. Okay, so there is, it's not that, I mean, one is significantly forward or anything like that. There are some of them have a lead. So photonics is definitely one of the technology which has the biggest, I would say, scalability advantage from the point of view that uh, it doesn't need low temperature like the way of many of the other technologies, or very high vacuum like other technologies. So yeah, so I think, but then there are challenges also that has to be surmounted. So we are putting all our effort to do that so that we can make it successful in the best possible way. And I mean, I would say that yes, I mean, if you're interested, come and join us.
So, Viman, one question I have, do you think you're doing more science or more engineering today in your startup?
I would say that 40-60. I would say that 60% is engineering now. 40% is still there is a bit of science that is there. Uh, but the things that you see, right, the touch and feel that we can see downstairs, the one that I was showing, those are, I would say, engineering. Okay, and where the science comes in is that some of the state generation and some of those aspects of it, how to simulate it in the best possible way. I mean, the physics of that, there is angle of science that is associated there. So, but I would maybe I would say 46 or maybe 30-70. I would say that 70% is engineering, 30% is science.
Okay. There's one question here. Other than optimization, what are other problems addressable using quantum computing? And anybody can answer here. Yes, please.
Well, I've
Maybe.
given this,
Yeah.
I've given intro talks a bunch. So, the ones that come that have probably the more near-term possibilities include what we call quantum simulation. So simulating quantum systems in nature using the quantum computers that we have. And that could be for purposes of understanding the physics or understanding chemistry, or trying to find the ground state energy of a certain arrangement of molecules or atoms, and things like that. So chemistry applications, um, high energy physics, those sorts of things are another class of algorithms that really were one of the fundamental inspirations of doing quantum computing in the first place. Because doing classical approximations of these highly complex quantum systems is very difficult, and you start making approximations and you need lots of memory and all that. So that's an area of very high interest. And you asked the question about AI. I mean, quantum machine learning is another one that comes up a lot. It's still I'm still a little bit on the fence about quantum machine learning, to be honest. There's no provable benefit to quantum, but a lot of people are spending a lot of time trying to understand, can quantum algorithms give you better solutions with fewer parameters? Can you get higher quality because you can explore the space and sort of get to an answer more quickly? There's some optimism about that. I'm not a machine learning person, so I have a hard time saying yes or no. It's absolutely going to be a game changer. But the combination of AI and quantum definitely is something that will happen. AI will help quantum machines, and hopefully quantum machines will improve either the speed or the quality of AI solutions. The one that and the final one that people talk about are things that are more numerically oriented, like breaking cryptography codes and things like that. Those I still think they're great applications, but I think you need very large machines to make an impact there. So I think that's still a ways off.
Thank you. So people have also asked for the research paper that you talked about. So Yasar, please do share that after this, talk with
Yes,
everyone.
sir. We have
Thank
shared it.
Okay. So anybody else wants to answer any other question which is
I
going?
think one good question is here. I think Professor Byrd could answer it very well. So there is this Indurkar, I think, Indukur. So I want to be chosen this is as a quantum computing as my career. Is there any specific course or studies? Sorry, I want to be in quantum tech. I'm from electrical engineering background. Suggest me the best field in quantum computing. So yeah.
I mean, as you may have gathered from this discussion, I mean, quantum computing is a very broad topic, and you kind of need to find the things. One thing that we haven't talked about too much here is all of the classical hardware, the control and electronics that goes into operating the quantum machine. And we haven't even talked about error correction and things like that. So from an electrical engineering perspective, it's sort of the electrical engineering itself is very broad. So you might be someone who specializes in control systems, which is very applicable to this space, or you might be someone who's done signal processing or information theory, and those they all bring their own kind of background that can be applied either to help build quantum systems that operate well, or to apply some of those concepts to the quantum algorithms. Because really, what we're talking about with quantum algorithms, it's sort of an analog digital kind of mix, and people that are very comfortable with the math involved with linear algebra and control systems and signal processing, they're very well equipped to understand the kinds of operations that you can do and characterize in a quantum machine. So if you're, if what you mean by electrical engineering is electronics, then all of this, photonics and integrated photonics and just the classical processing of data that you need to do error correction is something that you can find lots of avenues there to find the niche that you're most excited about.
I think I'll take one more. We can take two or three more questions, I guess. So there is a question, Rushikesh. Can you please ask whether someone with a 5-year career gap and after graduation, or someone switching careers from mechanical or another background, can enter in the field of quantum computing? So I would like to answer this actually because I myself is from mechatronics engineering background. So I studied few of mechanical, few of electronics, a little bit of computer science, and then I entered in this field. So yeah, definitely you can do it. And in the learning process, you can take some basic courses. If you are looking for a software perspective of it, I would say get your foundations very strong. Right now, Python has been used. Get your hands dirty on Python, get your head dirty on these concepts. Okay, then try to understand basic principles. As Professor Byrd said, you don't need to understand whole quantum mechanics, just few principles that are used in quantum computing. Okay, you will get all of these in some online courses. There is good course from Pact and Coursera, you can do that. Okay, and if you're looking for a hardware side, I think you need to do masters and you need to get a good understanding of hardware. And I think Biman could a little bit explore tell much more on hardware side of it. But I would like to just add that whenever you are learning this course in quantum computing, the best way is you are trying to learn by doing. Okay, if you are trying to learn algorithms, you should try to learn by trying those algorithms. So basic version, there are simulators provided, like you can use Qiskit, you can use Pennyline, all of these free open source libraries. You can just install, you can try to run this algorithm, try to solve some problems. And that's how I started. And all this develop, even the research paper of what we were talking so far about, it took nearly more than 1 year for me to get this good solution out of it. So it's like you are trying, we are failing, the constraints are not satisfied, you go. So even if you're not getting sometime, if you're trying to approach this as a research thing, so if you're not getting solution sometime, it's okay. You need to try it again and again, and we can land it. So I think Biman and I think Venkat sir, you can just answer about the hardware part. If you're someone travel like from mechanical side with some career gap want to go for, if they want to try it with hardware. Yeah.
I'll just pick on the one point you said, which is that you have to do, that whether it's hardware, software, whatever it is, you have to actually build systems, do things. Or even if you're a theoretician, you still have to go and solve, formulate some hypothesis, try and solve that. So that's the only way to learn, because you might read the book and it's very deceptive. You might think, I've mastered the book, I scored 90%, but until you actually go and try and solve something or build something, you will not you'll not be able to test yourself there.
And I can just add that, yeah, I mean, it's always possible. I mean, I had been, for about 19 years of my career, I have been doing electronics design and uh, of circuits, and then I switched. And of course, there was obviously a time when it was tough to exactly grasp all the concepts, and but then a lot of hard work has to go in. But yes, I mean, and I will getting the hands dirty is probably one of the, get quiz kit, try to do something funny. But yes, I mean, try something out and get some confidence around that, and then it becomes easier as we move and things start to fall in place.
Yeah, for concrete actions, I would pitch the IBM courses. The IBM has a lot of learning um, material. A lot of the companies do. Microsoft has a lot. Penny Lane is there. There's lots of resources out there for you to get your hands in it and try it. But there's a sort of very organized couple of courses, modularized courses that IBM has. So I think if you go to quantum.ibm.com or something like that, you start to see those things, and those are good. And IBM also has these summer school programs that are sort of a few weeks of very intense learning and examples, and those are the kinds of things that you can definitely learn on your own outside of class.
And I'll take over. I think we can take one more question. Uh, so there is a very interesting question by Tanmay, I think. So will quantum computing have negative impacts in future, similar to how AI has been used for deepfakes and other harmful applications? Could there be dangers associated with it in the when everything is quantum is in the place now? So Venkat sir, I think the best person you can answer. Yeah.
Venkat, I think you can answer that one.
Yeah, see, I think today everything is dual use. You pick any deep technology, it is dual use. You can use it for any kind of applications that you have. So I think that's a question to which the answer will come from us only. We have to create those guardrails. We have to create solutions which are going to tackle these challenges that you just mentioned. In fact, in AI, for example, deepfakes and many other things are there. But the solution to that also has to come from AI. It's not going to come from anywhere else. So I think that's it. I don't think there's a clear answer here. That's what I'm saying.
Yeah. Okay, I think then most of so Venkat sir, yeah.
Yeah, so thank you all of you so much. It was a very nice, brilliant session. I think we all learnt a lot today, and I hope the students also enjoyed it. The course that this session is part of is one of the largest in the world, 50,000 students. So all of them, I hope they build a career and go forward and enjoy themselves and contribute a lot. So thank you each one of you for joining us today. Thank you panelists. It was very nice to have you here with us today. Thank you.
Thank
Bye.
you.
Thank you.
Thank you. It was
Thank you,
fun.
everyone.
Thank you.
Rapid fire was really fun.
So Yasar, don't forget to share the paper with everyone because people are asking for that, right?
Yes,
Lot
sir.
of
We have shared in the chat as well as in the description box. we have added in both.
Thanks. Really enjoyed the session. Yeah, it was
Nice. Thank
Thank-
you.
so much.
Okay, bye. Bye, everyone.
Bye. Bye.
Bye.
Thank you. Bye. Bye, everyone.